Well, in this video, I will be using the 3D Experience Release 2022x and its finite element solver to show you how to do a modal dynamics problem. The problem under consideration is a bar-like object, which is axially loaded like that, and the cross section of the bar is 1 inch by 1 inch. The length of the bar is 200 inches. And the standard steel property for Young's modulus is used. And I'm assuming that Poisson ratio is 0, although you can use any other value, including 0.29 or 0.3, which is representative of steel properties. And because we are talking about the dynamic problem, the density is also given. It's here, and its units is in slinch per inch cube. Now, the purpose of videos like this is to show people who want to use 3D Experience's FEA solver how to do some very basic problem. These are not complicated ones, but it's a relatively simple problem. Now, you have to be aware of the limitations for modal dynamics, and the problem must be entirely linear, both as far as material properties is concerned, as far as the strains are concerned, and displacement, infinitesimal, and no contact stuff is allowed if you're going to do modal dynamics. And the reason is that this is based on the modal superposition method, and as soon as you say superposition, the problem has to be linear. Now, uh, there is something else that one should be aware of, and that is sufficient number of modes must be taken in a real problem, realistic problem. Sufficient number of modes and modes in the, which contribute directly into the deformation. Not only sufficient number of them, but also modes that actually has an influence on the nature of the loading and deformation. And very often, this is done internally by the computer using the modal participation factor that is generated. But our problem is simple, so we're not going to worry about it. Now, it's a good idea if one has a feeling for the theoretical development behind this method or any method that is being done with finite elements, and I suggest that you look at a respectful vibrations book. Now, here's the situation. The loading that we apply is going to be like that. It's not quite an impulse load, but you can think about it as something close to it. So the load starts from 0, goes up to 1,000 pounds, and then drops within this time frame. And of course, that will lead into dynamic analysis. Okay. Now, uh, I'm going to be comparing my generated values in 3D Experience with some stuff that is done in Logan's book. Although you have to be aware of the fact that I'm not I'm not claiming that what I wanted to get here, based on using two link elements or beam elements. We're not going to model this thing as 3D. I'm not claiming that I should get these values. It's just to give a rough idea of what Logan does based on two elements and lump masses. You get these natural frequencies, which are important. We're going to be using it, and the analytical solution, which is here. Okay. Now, what you see there is the blue one is what is generated in Logan using the central differencing and two elements and lump massing. Okay. In this tutorial, we're going to be using modal dynamics. It's the results are generated by that red graph, and I'm going to use only two modes and therefore two elements. Okay. This is to get you going to give you a feeling for how problems in modal dynamics are done. It is not. I'm not claiming that these should match because they're two different methods, basically. Okay. Now, uh, we'll come across an issue in the help menu later on, which I have put here in the software's online documentation. I could not get this thing to work, and therefore I did it a different way. Although don't worry about this thing right now. We're gonna talk about it later on. Okay, so as I said, I'm going to be using two one-dimensional bar elements or beam elements if you want. However, since I will restrain it so that it only axially deforms, uh, generally speaking, people call it link elements. Okay, so two elements, one here, 100 inches long, the second element 100 inches long, and then we're going to look at the displacement of the middle node, and you will see that. Okay, here is the 3D experience interface. So we're going to go to part design application, and our geometric model consists of a single line. So let me go ahead and create 2 points and then connect them with a line. So I go to essentials. First point is going to be 0, 0, 0. The second point is going to be 200 in direction y, 200 in direction y. And now create a point between a line between points 1 and 2, which I can do it from here. This line, this point, this point. There we are. And you can of course fit it. And it's going to show on the screen, right there. Okay. Now, so that I do not inadvertently put a restraint on these things, I'm going to hide this point and hide that point. Now I'm going to create a material. So I go to Tools, create a material. I'm going to call it Modal Dynamics Video. Okay, so we say OK. It's created by name here, but there is no Modal Dynamics Video, but this is just a template. There's nothing in it. So I'm just going to right click apply. I'm going to put it on this part, and now I'm going to input the values. So expand this thing, double click on it. So under structures, under general density, it's in terms of slinch per inch cube, so it's going to be 0.00073. Good. And then under abacus multiphysics, mechanical, elasticity, elastic, 30 million psi for Young's modulus, so 30 with 6 zeros, 1, 2, 3, 4, 5, 6, and Poisson ratio 0. Okay, I'm assuming 0, but that's no loss of generality. Okay, good. It really doesn't matter in this problem because you're using bar elements or beam elements, and they don't use Poisson's ratio anyway. All right, so that's it. Now we're going to go to the general structural model creation for meshing purposes. Use the empty FEA model on the right side. And now we're going to go to mesh beam elements. Select that line and put a size of 100. That will give you two elements, and these are linear elements, as you can see. Okay. We now create a cross section. So go to properties, make sure you use a link, 1D link section, and once select the line and 1 inch squared, 1 inch squared. Okay. Of course, the material property is selected correctly. Now, this is basically representation of the properties of that link. So I'm going to hide this. Hide it, right there. Okay, so we go to structural scenario creation. Select the finite element model that we created just a minute ago. All right. Now, our first task is to create the natural frequencies or extract the natural frequencies of the structure. Now, first of all, let's go to procedure and go to natural frequency or frequency step. Notice that what we want to do later on is modal dynamics, is this guy. Okay, however, it's dim because that requires the creation of the frequencies first. So we create we use the frequency step, and don't go to 10 modes, because there's only two modes. The way I'm going to restrain this bar, it can only move along the y direction, and there's only two uh, free nodes here. This one is at the wall. It's going to be fixed, so it's going to be maximum two modes that I can extract. So I changed it to 10, from 10 to 2. Otherwise, you come back and says we don't have 10. Anyways, so now under restraints, that entire line cannot move in the direction, cannot move, notice that I clicked on fixed displacement, cannot move in direction X or direction Z. Can only move in direction Y, like that. And that that node is the wall, so it's going to be another fixed displacement. This point here, or this node here, actually, it's not the point. Okay, and cannot move in direction Y. Rotations don't matter because this is going to be link element, does not have rotational degrees of freedom. Okay, now before I go any further, I need to create two manual groups here. Now that groups is done actually in the model. So let's go back to the model here. We're in scenario right now. Let's go back to the model. We create our groups, which I forgot to do. On the group right there, see that on the group, this tab, manual creation. Now let me do the following. Let me hide these restraints and everything because they're blocking my view. So let's see now. Where are the restraints here? Let me hide this. Okay, good. And I noticed that let me update. That's okay. So we go to manual group right there. I updated. There was a warning, but that's okay. So here is I select this node. You see that? This node right there. I use the manual group. There's the manual group. I selected this node. I'm going to call it middle node. That's where I'm going to be plotting displacement versus time. Say okay. And then I want one over here, wall node. So again, manual, this point, this node actually is going to be wall node. All right. Now that I created the groups, which I forgot to do initially, so I go back to scenario right there. I remember it was a frequency step and everything was done. There's no load in a frequency step, so we go simulate. First of all, we do a model check. Then I'm going to do a simulation check. It's a very simple problem. Nothing is going to go wrong. So, I didn't like that warning message that I got, but that's okay. It doesn't do anything. So I'm not sure what it was. I suppose when I updated the model, it just disappeared. Okay, so this is the model simulation check status. And then once this thing says successful, we're going to go and run it. And we're going to extract the two frequencies are going to get extracted. Yep. Now this is simulate, which we actually run it and calculate the two frequencies of interest. There are no more than two frequencies because there's only two nodes here, two free nodes, and they can only move in the direction y. That's why there are 2 degrees of freedom, two natural frequencies. And these should match Logan's, or should be close to what Logan got in the slides that I showed you. And it will be. You need these two frequencies in order to do the modal dynamics, which is the superposition of nodes. Not nodes, modes. Okay, this is going to be done there. Notice that you have two frequencies. One of them, the smallest one, is roughly 247, And if we check with Logan, you see that it's very close to that. And the second one is 596, which is again very close to what Logan had. Okay. Actually, let me bring that up. View modal dynamics right there. Okay, so you can see 258, 598. Okay, very close to what we got here. Okay, now this is done. So we go back to scenario. We go back to scenario setup or standard right there. There's a scenario. And this time we're going to create a modal dynamic step. See that before this was dim because we had not done the frequency calculation. Now it can be selected. So the total time is 0.01 and the time step, I'm going to make it 0.0001. Okay. This is the total time, which is in line with the kind of graphs that I want to get all the way to 0.01. And you have to read the theory part of the modal dynamics to see what the time increment is here. It's similar to this, time step if you want. Say okay. Now, what we're going to do is if we're going to apply this kind of a load here, okay, we need to create an amplitude function. And that is done there. If you go to the setup, see that setup tab in scenario, you go here, it says tabular amplitude. Make sure that you use the step time. If you inadvertently use the total time, there's no way to change it, and then you have to delete that. You have to delete that amplitude and do it again. So step time, not this guy. And this is a smoothing. So what that means is that if you look at this curve, there's a sharp corner here, there's a sharp corner here. If you say smoothing, it does a smoothing operation here. Put kind of some kind of a fillet here if you want, but I don't want that. I'm going to say 0. Okay, time 0, load 0. Times 0, 0.001, load 1,000 pounds. Oops, not 2,000, 1,000 pounds. Times 0.002, load 0, and then total time of 0.01. Of course, it's going to stay 0. And if you want to see whether you did it right or not, you say right click, you put the cursor in somewhere in one of these cells, and XY plot. Oops. Yeah. So what you see here is this thing is actually that graph. All right, good. So let's close this. We don't need this. Okay, say okay. Now we're going to apply a load of 1 pound here. So we go to load, force, on that node, 1 pound in the direction y, and not the default amplitude, tabular amplitude one that I inputted. And then we say, okay. Now, we're done. So if we say simulate here, if we do, for example, model check, scenario check, simulation check, and then run, we're gonna get an error message. You'll see why, and I want to show you why. Okay, so let's go ahead and see model check. You see that? It says, hey, you didn't ask for any output. Required output is missing. So we say, fine, get it. So close this, close that, and this is where you require output. So output, you click on the output right there. See that? And then we're going to do it by groups. Remember, we created 2 groups. Middle node. We want middle node. We want displacement, translational displacement, just translation. We don't need rotation. There is no rotation here. And at every increment, every step that we specify, remember 0.0001. Okay, at every step. Now I want this thing to be history. This is very important. History output, because we're doing it versus time later on. And this is it. Yep, this is it. We say okay. Now the other one, let's do another one, which is the wall, the end at the wall. So again, once again, it's a group, but it's the wall node. I want history output, and I want forces, reaction forces. I don't need moment because there is no moment here. And at every step. This is a very simple model. It really doesn't matter. Now, when we say model and scenario check, we're not going to get that warning message or error message. We do simulation check. Everything's going to go through. And finally, we will do a run, simulate the final step. Okay. So if you want to plot the stresses, displacements, and things like that, with with the color codes and things like this that you're used to in finite element, you have to ask for a field output, okay? Not history output. Okay, this is done. And this was the simulation check, and now we're going to run it. This is the actual moment of truth, whether it's going to run and create the graph that we want or not. We'll see. Yeah. Remember, I asked for the information at every step. If you have a lot of step, a very large model, a large number of points that you want to look at, then this can be very storage intensive venture. Okay, but we're talking about only one node here. Okay, maximum of 10,000 steps. Actually, 100 steps, right? Okay, that's it. All right. So first of all, this is for frequency step. If you go to model dynamics, uh, I noticed that something did not work. Okay, that's fine. Something that's bothering me here, but anyway, we'll find out. So let's go hit there. I wonder what I put for the time step here. Yeah, it should be okay. All right, let's go to the here results right there. Okay. Yeah. Now, plots, under plots right there, plots, history plot. And here we're going to say, okay, I want not everything. I want the translation, right here, translation. And this translation direction Y. So let's not do the magnitude. Let's say it really doesn't matter, but let's do the vector component 2, direction Y, and then say apply. Okay, so what you see here, this graph is that graph. Okay, right. Now, if you say, okay, can I have the reaction force at the wall? So you're going to change this thing to reaction forces in the Y direction. Apply. This is reaction force at the wall. Notice that the units, of course, change. It says 0 to 1500, roughly 1500, 1600. Now, notice that clearly is the dynamic effect here. First of all, because you can see that the load on the top and the bottom, they're not 1,000 that we apply. It's not 1,000 that we apply. It's more than that or less than that, either way, if you can look at the positive and negative. And that means that there's a dynamic effect. And it makes sense because initially when you apply the load to the right, rise the load, the wall says no, no, no. That's why there is a negative reaction force. But when thing goes, basically reduce the load to zero, then the wall doesn't like it, and it applies a force in the positive direction. So that's okay. Now, the other thing, by the way, yeah, so that's fine. Now, what I want to do is, let me close this. Let's see how many things that we applied here. Let's check that. We created two graphs. This last one is because I didn't close it, so I'm going to delete it. Okay, these are the ones that I just showed you. Translation uh, and reaction force at the wall. Now, if you activate, you're going to get translation of the middle node as a function of time. Now, what I want to do is I want to compare these with Logan's results, which is this blue graph. Now, it looks like I could have imported Logan's result as an Excel file and then somehow matched it with this, and I couldn't do that. But there is an alternative. So if you look at this right here, you can say right click export. When you say right click export, it says, okay, I'm going to create an Excel file for you. For example, you can select the format here, Excel workbook. With that name, say okay. So what it does, it creates an Excel file with this information in it. And in fact, if you select this entire in Excel, if you try to plot this, first column is time, second column is, or this column is displacement, and you say insert uh, graph. This graph that you see here is exactly what we see there. And now you can take for example, you can take the Logan's result and basically add it to this graph. So that's what I meant in my PowerPoint, saying that I could not do the import of the graph, okay? But I can do export. Anyway, that wraps up the concept behind modal dynamics for this simple problem. Good luck.